Hi, I'm Junho, and thank you for attending my session today. Let's discuss about the BUDAlloc defeating USET free bugs by decoupling virtual address management from Kernel. To ensure we are on the same page, let's quickly with the overall design concept of the USET free and one-time allocator. When we allocate the memory allocator assigns the virtual address and maps the virtual address to a physical address. After freeing the memory allocator retrieves the freed virtual address back to the memory allocator itself. At a later point, the freed virtual address might be reallocated to another object in the program. This is usually fine. But if the program tries to access the new memory using the old freed memory objects, an attacker could manipulate the memory, leading various kinds of malicious actions such as arbitrary code executions or control flow attacks. This is known as USET-free vulnerability. So USET free is a critical vulnerability leading to various kinds of malicious actions in unsafe memory language such as C or C++. For example, in 2022, Google reports that over half of the high-severity bugs discovered in the Google Chrome were due to USET free. So in this context, the questions how to detect and prevent USET free in a C or C++ unsafe memory language program should deserve programmers' attentions. A recent approach to detecting USET free involves using a one-time allocator. One-time allocator allocates an object on a single page around memory, typically defined as 4 kilobytes. When the object is free, the one-time allocator removes the mapping from the page table. As the object mapping is removed from the page table, any further attempt to access the freed object triggers a page fault, which effectively detects USET free. This mechanism detects USET free if there is no overlapped virtual address in the program. But what happens when we allocate a new object? Let's try to allocate a new object O2 and try to see what happens. The new object O2 is always allocated a new virtual address. This ensures that the default object's virtual address is not reused, thereby preventing USET free bugs. However, this mechanism suffers from the high memory overhead because this mechanism requires that every new allocation should have to charge on the new page-aligned virtual address. To mitigate this overhead, we can use a technique known as alias mapping. In alias mapping, the virtual address is divided into two parts, mainly two parts. The first one is a canonical virtual address, which is used by the allocator itself, and the second one is the alias virtual address space, which is used by the applications. If application allocates memory, one-time allocator first assigns a non-overlapping page-aligned memory from the alias address space and map the alias virtual address to the canonical virtual address. When a new allocation occurs, one-time allocator maps also assigns the non-overlapping page-aligned virtual address from the alias address space and map the alias virtual address to the same canonical address, which effectively reduces one canonical address across multiple alias address. Despite this use, the one-time allocator still can detect USET free by removing the alias mapping from the page table. The one-time allocator with alias mapping offers reliable performance and high precision of bug detections. However, several inherent performance limitations prevent its practical and wide adoptions. To better understand these constraints, let's deep dive into the details. The one-time allocator manages alias to canonical mapping using a user-level side metadata. This metadata must be updated both after each memory allocations. However, the kernel also manages the virtual to physical address mappings. Because user and kernel are isolated, user and kernel doesn't know each other's memory management space. The problem occurs from the isolation of this separation between user and kernel and associated performance limitations is known as semantic gap problem. To overcome the semantic gap problem, one-time allocator must issue costly system call for each memory allocations. What makes more serious is the global kernel lock involved in these system calls. Because one-time allocator requires the frequent execution of system call, this frequent execution of system call leads to this global lock becoming a major bottleneck, especially in the multi-threaded program. So in short, the semantic gap is a major constraint of the one-time allocator performance limitations. Existing one-time allocator can be categorized based on how they address this semantic gap. In Oscar, they batches the system call. However, they suffer from the low performance, and they also cannot support copy on write. In FFmalloc, they remove the alias to canonical mappings, but they suffer from the high memory overhead and low precision of bug detections. In DangZero recently, they removed the semantic gap by utilizing a library operating system. However, they suffer from the unavoidable virtualization overhead and level of compatibility because they have to be used with the virtual machines. So in short, none of the previous work fully balanced performance, memory overhead, precision of bug detections, and compatibility at once. So therefore, to develop a practical one-time allocator, we must bridge the semantic gap and achieve the optimal balance of these limitations. To address this, let's quickly review the overall design of traditional one-time allocator. Also mentioned earlier, previous approach relies on the system core to synchronize user-level metadata with the kernel. We can classify the design into the mainly two parts. The first components manage for the first component, user-level, manage the alias to canonical virtual address mappings, while the kernel it manages the virtual to physical address translation in the page fault handler. In BUDAlloc, we address the semantic gap by decoupling virtual address management from the kernel. This approach enables the kernel to handle page fault using a shared metadata directly in the custom page fault handler, thus eliminating system core overheads and duplicated metadata management costs from our allocator performance. However, this method requires the isolation of user and kernel pages. We use extended Berkeley packet filter to safely share metadata with the kernel. Extended Berkeley packet filter is widely used for safely injecting user logic to the kernel. For detailed information on our API design and detailed implementation and safety mechanism, please refer to our paper. With the user-level allocator managing the virtual address space, the kernel is only responsible for essential physical address management tasks. This separation of virtual address management from the kernel is what we term decoupled virtual address management. This is the overall design flow of BUDAlloc. First, we allocate a canonical address, followed by the non-overwriting page-aligned alias address. And then we update the shared metadata with alias to canonical mappings. When there is a page fault in the custom page handler, it leads the shared metadata with faulted alias memory and update the page table with customized eBPF helper functions. With this code design, BUDAlloc enables similar optimization unique to our decoupling design. In performance, BUDAlloc offers the option to defer alias freeing until the next page fault, which help to improve performance. This mode defers the immediate bug detection to the next page fault. We present this mode as the BUDAlloc prevent in the evaluations. In scalability, BUDAlloc eliminates the global kernel locks and supporting fine-grained locking using user-level semantics. In compatibility, BUDAlloc seamlessly releases all kernel physical memory management features, ensuring transparently ensuring broad compatibility with existing kernel functionalities. So to test the detectability of the BUDAlloc, we use a certain CVE benchmark set, something user-free CVE benchmark set for evaluating precision of bug detections. And BUDAlloc detects all attacks in the detection mode. As we mentioned earlier, BUDAlloc prevent default alias freeing for the performance. In the BUDAlloc prevent, it detects about 97% of the user-free in our CVE benchmark sets, while FFmalloc previous work shows only about 23% of detectability. The root cause of this difference is derived from the fact that BUDAlloc detection window is at least next page 4, thanks to our decoupled virtual address design. Despite this superior precision of bug detections, only the BUDAlloc shows the similar performance, memory overhead, and scalability result with a real-world web server like Apache. As the number of concurrent connections is increased, a garbage collection-based marker shows the worst performance because it requires the additional thread for correcting the user-free bugs. However, in the FFmalloc and BUDAlloc, they show the similar performance with the glibcs. In the memory overhead, FFmalloc shows about 70% higher memory overhead compared with the glibc as it batches the free. So in short, only the BUDAlloc shows the high performance, low memory overhead, good scalability, and superior precision of bug detection in our evaluation. So in summary, we decoupled virtual address management from the kernel using extended bucket replica filter. And by the decoupling, we remove semantic problem and introduce several optimizations such as fine grained locking. And finally, BUDAlloc shows the superior precision of bug detections, performance overhead, memory overhead, and compatibility and scalability compared with previous works. So thank you for sharing your time. I'm happy to take your questions.